Welcome to Spring LIB.
Our question says that copper and aluminum are being considered for a high voltage transmission line that must carry a current I of 60.0 amperes. The resistance per unit length is said to be 0.150 ohms per kilometer, which I then convert into ohms per meter. So I write our resistance as R over L is 1.5 times 10 to the minus 4 ohms per meter. And the densities of copper wire, which are 8,960, and since rho is commonly used for both density as well as for resistivity, I differentiate between them as rho m for mass density of the copper wire and rho ma for mass density of the aluminum wire. And then rho c is the resistivity of the copper wire, and rho a is the resistivity of the aluminum wire. Okay, so with all of this given, we're asked to compute for A, the magnitude of the current density, and B, the mass per unit length of the copper wire, and C, do the exact same thing, find the magnitude of the current density, but this time for the aluminum, and then D, find the mass per unit length of the aluminum. Okay, so let's start with part A. Well, resistance over length is equal to the resistivity of something over the area. Therefore, the area is equal to rho divided by, and since we're given R over L, we'll leave it together. Okay, and so now that we have the area in terms of things that we actually know, this is going to be useful here for part A. So the magnitude of the current density, J, for the copper wire is equal to I over A, right? And we just found what A is. So for the copper wire, this is going to be I times R over L. And then all of this is divided by the resistivity of the copper wire. So R rho sub C. Here, let's write it like this. Rho sub C. Okay. So you plug that into the calculator, and this comes out to be 5.32 times 10 to the fifth and the units here are amperes per meter squared. Okay, and we can box it in as our solution to part A. Let's redo that. Okay, let's start a new page here to do part B. In part B, we are asked to find the mass per unit length of the copper wire. So we call that lambda of the copper wire, which is equal to the density of the copper wire, so rho m times C times the area. And again, we already calculated what the area is, so this is rho mc times the resistivity of copper divided by R over L. Okay, so we know all these values here, so you plug in the value for the density, the resistivity, and R over L, and this comes out to be 1.01 kilograms per meter. We can box it in as our solution to part B. Now part C, we're doing the exact same thing we did for part A, except this time we're going to be using the values that were given for the aluminum. So we'll call this J sub A, and that's equal to the current over the area, but again, we know that the area is equal to the resistivity, rho A, divided by R over L, so then R over L is on top. Okay, so we plug those values in, and this comes out to be 3.27 times 10 to the fifth amperes per meter squared. Okay, and then lastly, we're asked to do the same thing we did for part B, except now again for aluminum. Okay, so this is going to be equal to the mass density of aluminum multiplied by the area, which is rho A, divided by R over L. Okay, we plug all these values into this expression, and this comes out to be 0.495 kilograms per meter. You can box that in as our solution to part D.